How's everybody doing? First ever inaugural C++ Under the Sea. You guys enjoying yourself?
Yeah.
All right. Well, thank you for having me. My name's Conor Hoekstra. I go by code_report on the internet. And welcome to my talk, Arrays, Fusion, and CPUs versus GPUs. I didn't exactly know what to title this talk because there's a lot of points and things that I wanted to cover. So I just threw a bunch of stuff and comma separated it, threw an ampersand in there. But hopefully you're going to enjoy. I imagine there's going to be a lot of questions. If you do have questions throughout the talk, feel free to throw your hand up. I can repeat it for the audience, or I guess the audience on YouTube. Or you can wait till the end. I'm hoping to have at least 5 minutes, if things go amazingly well, even 10 minutes for questions, because I'm going to show some profiling performance comparisons at the end. And whenever you do that, there tends to be a number of questions. So this is the About Me slide. We're not going to spend too much time on this. The important stuff is that I've been in the industry for about 10 years now, and I've primarily been a C++ developer for the entirety of that time. In the last 5 years, I've become a massive fan of array languages. If you've heard of APL, that's probably the most famous of the array languages. If you listen to any of my podcasts, you will know that, and we will get to see a tiny bit of array code. A lot of C++, we get like 2 to 3 minutes of array code. I have 4 podcasts. The one on the left is the one that is probably most well-known in this room. Bryce, the co-host, is sitting in the first row. We're at 204 episodes. We just released episode 203, zero indexed, which is why the numbering does not match up with the total number of episodes. But I've also got a couple other podcasts. The 2 middle ones mostly focus on array languages. I do a bad job of highlighting this, and I got this feedback that people didn't even know that I was the same person behind this YouTube channel. So now I try to highlight that more, just so that folks know that if you've seen any of these one problem, 24 programming languages, sometimes I do. The second most popular video was this from C to C++ to Rust, and then Haskell, because Haskell also influenced Rust. Anyways, I think I've got like 350 plus videos. I erratically upload. When I first started the YouTube channel, I would upload, once every 2 or 3 days. Now sometimes I go 8 months without posting anything, and people are upset. But anyways, if you like this talk and you are looking for other content, I do post stuff to my YouTube channel under Code Report. So everything I just mentioned, you can find under a GitHub repository called Content. Also, too, I know this is a big room, and it might be hard to make out some of the slides. There is a PDF copy of this slide deck if you go to content/talks and look for 2024 C++ Under the Sea. If you're at the back of the room and you have a laptop and you want to follow along, the slide deck I posted, I think, this morning, and all the example code as well, you'll find at this repository. So we're going to start off by introducing a problem. And then the goal of this talk is to solve this problem mostly in C++, but we're going to look at a couple different languages, Rust, Swift, Python. And the majority of the solutions we're going to see are going to run on the CPU, but then there's going to be 2 or 3 that run on the GPU. And this is intended as an introductory talk to if you've never targeted a GPU in terms of trying to accelerate your code and you want to get started. I get this question all the time. I was at a functional conference called Lambda World a week and a half ago, and I got the question like 3 or 4 times. I want to accelerate my code. What do I do? And my first question is what language are you starting from? It is a completely different answer if you're in Python versus if you're in C++. So I'm going to show a couple different strategies. And then at the very end of the talk, after we've looked at a comparison of all these solutions, we're going to not benchmark them, but show a relative comparison, at which point I'm sure, people will have questions. But first, what is the problem? This is one of my favorite go-to first things that I ever code in a programming language when I'm learning it. I call it RMMI, or for short, RMI, and this stands for Reduce Map Iota. So, technically in C++ land, you might actually call this Reduce Transform Iota, because we call our transform, or our map transform. But essentially, it is generating an iota sequence. Hands up, those that are familiar with iota as an algorithm. That is about 60% of the room. So good job for knowing your algorithms. Iota is just a fancy word. It comes from APL, actually, from generating a sequence of integers that increase by 1. So 1, 2, 3, 4, 5, 6, 7, 8. And technically, in the iota algorithm that we have in C++, you can specify your starting integer. So you generate this sequence of numbers. You apply a number of scalar transformations. So in our example, we're going to do modulus 10, multiply by 2, add 1, and then once you're done those transformations, you just reduce that. So there, probably you're thinking in your head in C++ or your language of choice, but we're at a C++ conference, so I'm guessing for most of you that's C++. There are a variety of ways to solve this problem. And we're going to start very simply with no algorithms. Very sad face for no algorithms. But we're actually not. So I forgot. We're going to do this in BQN. So live code, I think the next slide says we're going to live code this. So this is the 2 to 3 minutes in BQN because this is the best way to solve this problem, in my opinion. So this is a online web editor similar to Compiler Explorer, if I'm assuming you're all familiar with that. And it's interpreted, though, so it's a lot faster. It doesn't have to compile. So we're just going to do this with 10. So the first thing we want to do is our IOTA sequence. In BQN, so BQN, for those of you that don't know, I'm putting the horse in front of the cart, it is a modern APL. So APL is a symbolic language that uses Unicode symbols to program. And BQN was supposed to be APL with each of the letters incremented by 1. But if you're thinking that's not BQN, it should have been BQM, they messed that up. But then they had already backronymed it to big question notation as a joke, and they liked that acronym, so they decided instead of +1, it'll be plus Fibonacci, is what BQN is. So that's a little fun fact about BQN. It's my favorite array language because it's a functional language as well as being an array language. So in order to get an IOTA sequence, they have an algorithm. Is this terrible to see? Is it better if I do that? That's better. Okay. I apologize for the folks on YouTube. There's a little bit of light wash in this room, so this is better. So IOTA sequence is this. That's called range in BQN. And then if we want to do a modulus 10, we do 10 with a pipe. The pipe is your modulus operator. If we want to do 2 multiplies, we just do 2 multiplies. If we want to do 1 plus, we do 1 plus. And at this point, we have our first 10 odd numbers. And then we just want to do a reduction, which is a plus reduction. Fantastic. This is why we love BQN, because it is incredibly terse. And you might notice this is evaluating right to left. That's one of the odder things about array languages, is they don't read left to right, they read right to left. But it's still linear, so if you're used to reading linear code, this should be pretty easy, other than maybe the range symbol. That kind of looks a bit odd. But the pipe, the multiplication, I mean, it's quite nice. You think about every programming language out there, except for symbolic ones like APL, we don't have the multiplication symbol. In fact, it's not even consistent across programming languages. We have plus, we have minus, we kind of have divides with the slash, because there's multiple symbols for divides, but we don't have multiplication. And so we have to use the asterisk. It's kind of irritating that we don't have, and it's such a basic thing that we learn in math school, but it's not on the QWERTY keyboard, so we don't have it. Anyways, this is the example that we're going to be solving. So now we're going to go to C++, and the first solution we're going to look at is our for loop solution. So hopefully, this should be understandable for everybody. We've got integer, res, short for result, and then we've got an integer-based for loop, and we're doing all 3 of our transformations in this line inside our for loop, and then just returning it at the end of the day. So I did see in Bjorn's talk, if you're at the conference and not watching this on YouTube, that Bjorn actually made use of the C++ 23 print library. And I have seen, I think in every other talk, that we still use std::c out. And it irritates me to no end that we have this beautiful new printing library, but we never use it in our examples. And except we're always showing like the cutting edge, bleeding edge of C++ stuff, but then we still use std::c out. So this is available. I'm using GCC 14.1. I think print is available since GCC 13. I could be wrong though, but with 14.1, the one that I'm using, it is definitely usable. And so that's just one of my little pet peeves. Use print now that it is available to us. So who can guess what the first change that I'm going to make to this code? It's still a for loop at the end of the day.
Range iota? We use iota?
Yes, I heard from 2 different individuals, both in the front row. Range is iota. So some of you might have been thinking, oh, I can switch to a range-based for loop, but you can't actually because we need the integer. So we are switching to a range-based for loop, but we need to make use of C++ 20's views iota, which gives you this sequence. Some people see this code and they don't like it. I obviously prefer it because I prefer algorithms and I have a soft place in my heart for iota. But effectively, these are the same things. Next, we are going to switch to the algorithm version of this. And this might be hard to see at the back, but hopefully people are going to be able to make this out. So for those of you that can't see, we are in pre-ranges land. If you go to the GitHub repository that shows all the code examples, this is called pre-ranges. And so we're making use of 3 different algorithms. IOTA on the 2nd line, transform on the 3rd line, and accumulate on the 4th line. What's irritating about this code? There was a response in the front row that said, everything. The number one thing that I was looking for, which I did hear from Kuhn at the end of the first row, was that it allocates. At the end of the day, all we're doing is like a for loop reduction. But in order to make use of our algorithms here, aka std : iota and std : transform, I need to allocate something into array, or a vector here. So not great, but this does the trick. Anybody know the next piece of code that I'm going to show? Slight improvement upon this? I think there might be one range, but it's not a full-blown range. It upgrades an algorithm. It switches to a different algorithm. Transform, reduce. And it actually does not. So I think the next slide is the introduction of our first range other than the iota we saw. So we can combine, if we look at this previous one, which is getting harder and harder to see as the light increases, we can combine this transform and this accumulate into a single call to transform reduce. So transform reduce has 2 different overloads, or at least the ones that we're concerned for. So this one is the overload that takes a binary operation as its reduction and a unary operation as its transformation. So we basically can fold our transform and our accumulate into a single transform reduced. The next slide, someone called out ranges before. This might be hard to see, but we're replacing our first call to std : iota with a call to std : views : iota. And now at this point, we no longer have an allocation for our vector. We're building up this sequence, this generator of integers, passing that as the range to our transform reduce algorithm. And now we've avoided the vector that we needed in order to use the C++11 std : iota. However, we're not going to see transform reduce because this used to be one of my favorite algorithms, and now it irritates me. And it's because this is a manually fused algorithm. The library and the committee has given this to us because it's a very, very useful algorithm, but it irritates me that in order to get this fusion, I have to manually reach for this fused thing. I want to live in a world where I can just compose things together and this fusion will happen automatically. As long as I reach for the right algorithms, I shouldn't have to reach for a transform reduce. I should reach for a transform, reach for a reduce, and if I use them together, it should just automatically compose. So we're going back to this solution, and for the purposes of the rest of this talk, we're going to look at this code. So what I did there is I changed my single call to transform to 3 different calls to transform. I thought about going through and putting a little emoji with a sad face. So I'm not advocating for writing your code like this, but this is highlighting that this is even worse than the original everything is terrible at this code, is because now we have 3 different passes because of 3 different transforms. And like this code irritates me because we should have libraries that are smart enough to know that if we're just doing maps or transforms after each other, these can just be this should be semantically, or it is semantically the same thing, but it should be iteration-wise and efficiency-wise the same thing as the previous code that we saw, but it's not, at least when we're using C++11 or C++20 range algorithms. But we're going to switch to views in a second, and that's where we live in the world that I want to live in. So right now we're pre-ranges, and now we are in C++20 land, post-ranges. And so, like I said, this should have a little sad face emoji in the top right-hand corner. Please don't write your code like this. But this is highlighting that whether we write our code like this with 3 views transforms or with a single one, this is effectively the same thing performance-wise and semantically. So sometimes depending on if you've got, right now we're just doing simple scalar operations that can be combined into a single lambda, because it's just 3 different lambdas. But you can imagine you live in a world where you might have some function objects that are a little bit harder to compose, and it's just easier to call 2 views transforms in a row, and you can call to those function objects instead of having to build up a lambda that then, you are manually kind of composing those. If you just have 2 different function objects, it might be easier to write a views transform passing that function object, followed by another views transform passing that function object. And this is why I really, really like this code. It's making use of views iota. We've seen this a couple times now, but now we've replaced our transform algorithms with transform views. And these compose beautifully. And the one thing that I haven't highlighted is that we're passing this all to a C++23 algorithm that is called fold left. So fold left is similar to std accumulate in C++11 and std reduce in C++17, the parallel version. But it enables you to pass a range directly as the argument, because one of the things the committee has not gotten around to doing is creating range overloads for the numeric algorithms. So in C++20, we got range overloads for, I think, 100 of the 105 algorithms that are in the algorithm header. But the numeric algorithms that live in the numeric header don't have overloads yet. But we have these new fold algorithms. So there's actually 4 of them. There's fold left first, where technically I could use fold left first here. Note that underneath the 3 views transform, I'm passing an initial value. So this is going to give me back, regardless if my range is empty, it's going to give me back 0 in that case. But if I use fold left first, it's going to give me back an optional. So sometimes you don't know what your initial value is. In that case, you can use fold left first, but then you're going to get back an optional. So in order to use that here, I would have to call dot value in order to take out that value. So pick and choose when you want to use fold left versus fold left first. And I believe there's right versions, fold right and fold right first analogs. And I believe there's actually 2 other ones that are underscore iterator versions. So instead of giving you back the value, you can get back the iterator, similar to other algorithms like find if. So if you're trying to implement like a find if using these fold left functions, you need to reach for fold left iterator. So a little digression here. We're going to take a trip to Compiler Explorer, and maybe I will switch this. I know Jason in the keynote this morning, more to settings, thank you. And we're going to go to same as system light. Hopefully this will be a little more readable. So how many lines? We're using -02 GCC 14.1. You can't see it because off the screen. Take my word for it, though. How many assembly lines do you think we've generated here based on this code? 200. The answer is 4,000. 3,872. And so I was going to ask, who knows what they think this is caused by? And I got 2 different people from the crowd saying print. So if we do a little live coding, and instead of using print, we just use the Jason Turner trick of returning this from main. If I type that correctly, it'll compile. And we are now down to 30 lines. I heard that there was like a promise of the print library that it was supposed to basically be a hygienic version of the printf stuff, which typically leads to lower, assembly instructions generated. So I don't know what's going on here. But yeah, I just want this to be in the canon on the YouTube, so the folks on the committee can see that there might be some work here to be done. Because even though I do love print, it's the f-string, pretty printing that you get from Python, except in C++. Anybody know how we can actually get this down even further? Const expr. So if we go over here and type const expr, let it compile. Not as good as the demo that Jason did several years ago on a Commodore 64, but still quite nice. All of the views that you use are designed to be const expr. So if you design this correctly, sometimes it compiles down to nothing. And if you're ever using a vector where you could use an array, one time I posted something on Twitter and it generated like, I think 12 lines, and then Eric Niebler came along, the creator of range v3, which inspired the standard ranges and said, hold my beer. He changed my std vector to a std array, and it went down to nothing like this as well. So anyways, end of the digression. The point being, for the committee folks, what's going on with print? A little bit sad there. So this is the Gobble link if you want to go play around with that later. End of digression. And this brings us to the comparison portion of our talk. So we just saw a bunch of standard C++ across varying different standards. You know, we saw, I think, C++. I mean, all of it technically was C++ 23 because we were using stdprint, but modulo stdprint, some of that was C++ 11, some of that was C++ 17, and the rest of it was C++ 20, modulo the stdprint. But now we're going to look at a bunch of different languages. So we're still going to stick with C++ first. We're going to take a look at, I think, 2 different libraries. Then we're going to move to Rust, then to Swift, and then to Python. And within those languages, we're going to take a look at a couple different libraries. So if you're not familiar with the symbols at the bottom, Thrust is a parallel algorithms library that NVIDIA produces. It's open source online. We're going to take a look at that. The N in the middle, anybody know what that is? NumPy, I heard someone say. That is correct. And does anybody know what the cube that looks kind of like the N on the right? This is the CuPy logo. So CuPy is a CUDA accelerated version of NumPy, which we're going to see when we get to the GPU examples. So just for posterity, the versions I mentioned, GCC 14.1 is the compiler I've used for all of the C++ code. When we get to the Thrust example, I'm using MVC CUDA 12.5. And when I get to the stdpar MVC++ example, this is 24.7. You can get that from the NVIDIA HPC SDK online. Rust is 1.81. Swift is 5.10. Technically, I think Swift 6 just got released in September, but I did not go and update that. I don't think it's going to change anything. And Python is 3.12. So this is the go-to ranges example with the 3 transforms. Once again, write it as a single transform, but for the purposes of the talk, we're using 3. And we are going to change this to range v3. So range v3 was the inspiration library that was used as a reference when standardizing the standard ranges that we now have in C++ 20 and C++ 23. The only change is a header and a namespace. In years past, this would have looked much different because there wasn't one-to-one parity, and there still isn't. But for everything that's used on this example, you just change the std : views to ranges : views, and the std : ranges : in front of fold left to ranges : and that's it. And if you didn't realize this, because for many years when I was writing range v3 examples, I would go and include each header that corresponded to each view and algorithm. There's like a shortcut /v3/all. Don't use this necessarily in production because it can blow up your compile times. But if you're just trying to put together examples and you don't want to worry about including individual files, use this. So nothing really to notice, but we are going to benchmark these, which is why I'm showing this code. The next example, I believe, is Flux. So who here has heard of Flux? That is about, I think, 5 or 10% of the room. So Flux is a library written by Tristan Brindle, who lives in the UK. And it is I would call it a sibling library compared to ranges. It uses different techniques under the hood, something called cursors. And it has a different API. So we don't, like in rangeland, you have to overload the pipe operator in order for you to get that kind of composability that we saw. Flux uses a different sort of method chaining. So if you're familiar with Swift or with Rust, this is more similar to the kind of style that you'd see. But other than that, and a couple naming differences, he uses the correct name map instead of transform. It's basically doing the same thing. So you can find all the links to libraries and technologies that I mentioned in the same GitHub repository if you want to go and check this library out afterwards. I think the next slide combines a library of mine with a library of his, because I really like the Flux library. So this is a library called Blackbird, which gives you access to a bunch of combinators and convenience functions. So one of the things when you come from languages like Haskell and array languages is, what are we doing here in these lambdas? We're taking a binary operation and partially applying a single argument. In the case of multiplication and addition, those are both commutative operations, so it doesn't matter which way you partially apply your argument. Modulus is not a commutative operation. 10 modulus is different than modulus 10. The same thing with division, subtraction, and so you need to apply the 10 on the right. But in order to partially apply something to a single character, plus the % for modulus, an asterisk for multiplication, I have to spell bracket, bracket, paren, auto space, a name for my variable name, n paren, brace, space, return, a variable name, then my binary operation, then my value, semicolon, end brace, end parentheses. That's ridiculous. When I'm trying to do something extremely simple and fundamental, the partial application of a binary operation, you're doing it all the time. And in order to do this, like, it's better than what we had originally back in C++ 11. We had std : bind something, and then we got bind front and bind back. And anyways, there's like 6 different ways you can do it. All of them are painful. So I make use of this. I wouldn't necessarily say go and sprinkle this into your production code. You're probably going to upset people in PRs. But if you find yourself wanting to reach for these operations, you have to include this namespace combinators. But I love sprinkling this into my own code. Question?
So the underscore indicates where the value will be?
Yes, I skated by that, but a question from Flores Bob was, the underscore indicates where you're partially applying. And yes, that is the case. So for commutative operations, I actually only provide the prefix one, because it doesn't matter, right? But for non-commutative operations like modulus, I provide you the one with, that is basically, so there's underscore, mod, underscore. So with both a prefix and suffix underscore, and that is basically just a shorthand for a lambda, a binary lambda that is a wrapper around the modulus. So if I need the actual binary operation not partially applied, it takes me 5 characters. And then if I want a partially applied one on the left or the right, I just choose the one with the prefix that corresponds to that one. This is actually irritating because I have a sibling library in Python called dovekey that provides the same kind of things, but they have like a idiom for using prefix and postfix underscores, so I can't use those. But in C++, the only danger is if you have double prefix underscores. Single, technically, it's still a little bit sketchy because some people use it for like member variables and classes and whatnot. But I know what these mean when I'm using it in my code. And like I said, I don't sprinkle this into production code, but whenever I'm writing my own code. But yeah, great question. The next example, where this is just going back to the Flux, so that was just a plug for Blackbird. I think the next example is the Rust code. So Rust, in my opinion, it's a little hard to make out right now, but is phenomenally beautiful. It uses the right name for map, which is map. It has a much terser lambda syntax, and it comes with a sum method. So Rust, say what you will about Rust, and it also has, the print macro similar to what we got in C++23. Pretty fantastic. I think I have a digression about Rust code. So when I initially, and I always do this, because I dip in, at one point I wrote a library in Rust that was several thousand lines of code, but that was like a year or two ago. So every once in a while I'll go and write some Rust code, but I forget the idioms and whatnot. And so this was the initial, this is what I just showed. This is the initial code that I wrote though. I have a return in front of my expression, and in case you didn't see the animation, I added a dot into underscore iter after the range that I was creating. So the dot dot syntax, or dot dot equals if you want to do an inclusive range, is for generating a range. So that's the equivalent of our views iota in C++. But typically, whenever you have a vector or some kind of container that you want to call iterator functions on, which is like this map and this sum, there's a bunch of them in a standard library called iterator. You include it by going, include std : iter, or I don't think it's : but whatever the syntax is in Rust. You typically have to turn your vector into an iterable thing that you can call these functions on. You have to go into iter. But a range already is in that state. So it's unnecessary for me to call this, as it is to use the return. The last expression in a function, when there's no return or semicolon, is going to be returned automatically. And there's a lot of languages that do this. I think Ruby does this. And so I initially wrote this code, and anytime I write Rust code, they have a built-in static analyzer called Clippy. So if you run cargo Clippy, it then gives you the following: unneeded return statement. And it also says unnecessary dot into iter because it's already, a range is already, doesn't need this conversion. And not only does it have cargo Clippy, you can just run cargo Clippy -- fix, and it automatically goes and changes your code. So like, this is a plug, and I'll mention it again at the end of the talk, is like, we have this stuff in C++, but it does not come out of the box. you have to go and manually set up your formatting with Clang format or pick your tool of choice. You have to go and manually set up, Clang tidy and include what you use and CPP check. And I'm sure there's like 3 others that I'm forgetting. There's a bunch of companies that are built off of like this tooling that you have to go manually configure. Everything comes with Rust. I want like the equivalent of what Rust has, but just in C++. So I can do a single, curl command. It sets all this stuff up for me because we do have some of this stuff, but it's just not as nice an experience. The tooling in Rust is super fantastic. Anyways, that's my little Rust plug because I don't know Rust anywhere near as well as I know C++. But I always feel like I can just go around and break things, and I know that I'm not gonna, double free something, and the tooling just makes me feel like I'm here in C++, Rust is here, but like the tooling makes me feel like this much. Whereas I feel like sometimes it's the opposite in C++. You're just smashing your head against the compiler, being like, I'm supposed to, know this language. Anyway, so this is Rust. I think the next example is Swift code. So honestly, if you go back to the Rust and you look at this animation, super, super similar. Slightly different Lambda syntax. So they've got this $0 for a reference to your first variable in your Lambda, whereas we have the what they call, I think it's called something toilet something. If you look at the Lambdas in Rust, you've got the pipe. I don't really see it, but that's what they've got nicknames for stuff. And in Swift, this is your map. They don't have a built-in sum, but you can get it with reduce and an initial value. Note though that this is not a fused or lazy. So this is not technically the equivalent of piping the views and the iterators. So those are all fused libraries. This one by default is not, but you can switch it to be fused by adding a .lazy. So anytime you have these sequences, you can add a .lazy to the first thing in your sequence, and that turns it into a fused operation, which is interesting. Yes? So we'll talk about this when we get to the kind of benchmarking, but when you think about when we were making calls to each of those 3 different transforms in the C++ example, those are separate operations. But when you are composing the views, these technically don't get invocated until we pass this to the fold left. And so when you have 3 separate transforms in your C++11 algorithm code, you're doing 3 different passes and like 3 separate operations corresponding to each transform. Whereas when you have 3 views that are piped to each other, these basically are all done in a single pass. And that's the same thing with the Rust iterators, and the same thing with Swift once you put the .lazy on. But without the .lazy, it's going to do a single pass for the first map, a second pass for the second map, and a third pass for the third map. So you end up with performance implications, and iteration-wise, it's different. And Flux also follows the same kind of lazy model where it fuses stuff together. So moving on to the next slide, I think we're getting to our Python code now. So if you're familiar with Python, we have a generator expression here inside of our sum function. We're using our range function to generate our elements from 1 to n, and then we've just done our 3 transformations in here. So we're going to look at NumPy code next, which is somewhat similar but somewhat different. So no longer do we have a generator expression. We're making call to a NumPy function called arange. That's the equivalent of iota in C++. And note here that you are able to do binary scalar operations on the array. Here we had a generator expression, which the only difference between a generator expression and a list comprehension in Python syntactically is the brackets. So if we were to put brackets inside the outer set of parentheses, that would actually be constructing a list comprehension and then passing that to the sum function. But that's not efficient. We don't want to do that. We want to leave this as a generator expression and pass it to the sum. Here in the NumPy example, we're building up an array of 1 to n. Then we're doing modulus 10 times 2 plus 1. And each time, we're doing like new allocation for a new array, which is how array languages work in general. Which, once again, when we get to the performance and profiling, you'll see the implications of this. How do we convert this to run on the GPU? In this case, we change our import statement from import numpy as np to import CuPy. Ooh, there's a small bug there. That should say cp. And then it's cp.sum and cp.arange. Everything else stays the same. Technically, I could have just changed the numpy to CuPy and left it as import CuPy as NP, and that's the only change. And so in general, my advice to folks that are in Python is if you're using NumPy or if you're using libraries like pandas, those are the two most popular, but there's other ones, scikit-learn. In general, there is a CUDA accelerated library that's already written for you. In the NumPy case, there's like two different ones, and there's actively more being written. CuPy is the easiest one to get your hands on. There's one at NVIDIA if you're doing large-scale computing called CUNumeric. Pandas, we have a team at NVIDIA called Rapids, and they make a data frame library called cuDF. That's the Pandas equivalent. They do have cuML, which is the scikit-learn. Basically, NVIDIA's strategy for accelerating Python, or one of them, is that we just saw all the libraries that Python folks are using, and we said, we'll go take this and make a GPU version so all people have to do, for the most part, there's not one-to-one parity in all of these, but for very simple cases like this, all you have to do is import, well, not just import, you also have to go pip install and install the library. But pending that you have the GPUs to run this on, this works. So for me, it was just a matter, I already had CuPy installed, so when I wrote the NumPy example, I just changed the imports, and then it worked. Next up is Thrust code. So we're not going to show, I mentioned that transform reduce, we saw it once and we weren't going to see it again. You might think that because Thrust is a parallel algorithms library and it closely mirrors what's in the standard algorithm library that you could use transform reduce here. But like I said, transform reduce irritates me. I just want to be able to do things and have it automatically parallelized. So here, it's going to be hard to see this at the back of the room, but we're making use of two different fancy iterators. One is called a counting iterator. That's the equivalent of a views iota. And the second one is a transform iterator. And each iterator is used as the input to the next iterator. So the counting iterator, we're calling A, and we use that as the first argument in the transform iterator on the second line. And the same thing for the second transform iterator and the third transform iterator. So once we have this chain of iterators, we just pass them as the two iterators to std reduce, or thrust reduce in this example, and then you're good to go. And note that at the top we have all the includes that you need to run this. The astute viewer might see that one of the imports or includes changed from print to IOStream, and that's because currently I don't think CUDA supports std print. You might be able to hook into a GCC toolchain and pick that library up from somewhere else. I think I tried to do that though, and compilation didn't work, so certain libraries on the cutting edge don't work with the CUDA compiler. Next up is a version of the 3 views transform that we saw, except now we're passing this to std reduce with an execution policy. So this is standard C++ code run on nvc++, a compiler made by NVIDIA, and all you need to do is get the compiler from the internet, NVIDIA HPC SDK, if you search for that, or go to the GitHub repo, there'll be a link to it. You download it, and then you compile this like you would with GCC, and you pass it a stdpar flag, which turns on automatic parallelization. And as long as you've passed an execution policy as the first argument to one of your parallel algorithms, this code will work. So this is with C++ views. Standard C++, automatically accelerated. And I think with a perfect amount of time left, we're going to get to the profiling. So I've just shown you a ton of examples. How do they stack up against each other? So it's going to be hard to see this at the bottom, but this is for, I believe, 100,000 elements. And so we're going to look at 2 different sizes. The next slide is for, I believe, 100 million elements, and this is for 100,000. And at the bottom end here, I'll read them out in case you can't see at the back. It's Rust iterators, C++ flux, then C++ ranges, C++ range v3, CUDA Thrust, Rust parallel iterators. I didn't show code for that, but it's in this graph. Python Itertools, then Swift, BQN, C++ stdpar, Python NumPy, and Python CuPy. I skipped a couple because we're not going to talk about those. The order that these are in isn't super important. What I really want to highlight here is the stacked columns. The main takeaway, in my opinion, from this graph is that every single fused library is on the left. So NumPy and CuPy are fantastic. NumPy is probably the single most popular library in the world because it's the single most popular library in one of the most popular languages in the world. NumPy might be the most downloaded, used software library in the world. I don't actually know if that's true, but it's probably in the top 3 for sure. NumPy, though, every single time you call an operation, you do a +1 to an array, it allocates a new array. So when you look at the NumPy column, which actually I think I set this up, so, well, let's quickly turn this onto laser mode. So this is NumPy right here. And you can see we've got 1, 2, 3, 4, 5. Reduce, map, 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 and iota. Every single one of these has its own operation. There's no fusion. And the same thing with CuPy. CuPy is great, gives you an easy way to accelerate your NumPy code on the GPU, but also it's over here. And because in general, if you have not enough data, GPU performance is going to be worse. There's an overhead of getting your data on the GPU. So until you hit a certain threshold, typically the GPU computations are going to be slower, which we'll see when we look at the 100 million data size. But CuPy is the same thing as NumPy. Every single time you do an operation, a map, an iota, a reduction, none of that is fused. Whereas we look at all these libraries here, Rust, C++ Flux, ranges, range v3, CUDA Thrust with the iterators, and even Python Itertools. All of these are faster than the ones, technically, except for one of them. But that one's OpenAI Triton, and we're not going to talk about it in this talk because we don't have enough time. But in general, that's the main takeaway, is fused libraries end up generating faster code. If we take a look at 100 million, this is where the GPUs and the parallelism start to show. Well, it technically starts earlier than that, which we'll see in a sec. So CUDA Thrust is number 1. Number 2 is actually the parallel iterator Rust code, which is basically a similar version of what we saw. You have to make just small tweaks, and instead of going into iter, which you technically didn't need to do, you go into par iter. But it's not as easy. The Rust folks, they like to show that like all you need to do in your chain of functions is at the very top, similar to the lazy thing in Swift, you just insert this into par iter and you're done. That's not true at all. It completely changes the APIs of some of the functions. Reductions no longer work the same way. You have to pass these things called zero argument lambdas. So it's great in terms of perf, but it's not as easy as just injecting this one little thing in your Rust code. But once again, even at this 100 million element size, you can see that everything that's fused is on the left and everything else is on the right. So you're definitely not going to be able to make out this next slide. Well, this is just a combination of the two. But this slide is a summary of all of the backends that I've profiled, or languages that I've profiled, across 1,000 up to 100 million. And you won't be able to read this. So what I've done is one by one, we're going to go through. So this is the IE3. This is still hard to make out, but at the top here, we have the top C++ is always C++ Flux. So that's one of the takeaways from this talks. Flux outperforms ranges across the board, which is unfortunate, in my opinion, because we standardize ranges and not the Flux model. So we're at 1E3 here now, but let's go one by one. So what are the changes we're going to see? And so note that at this point, Python is one above NumPy, but if we go to 1E4, for the rest of the examples, NumPy is now more performant than Python. Another one of the takeaways of this talk is that because NumPy under the hood is implemented in C, it's almost always faster than any kind of Python Itertools or generator expressions. Anything that's written natively in Python is slower than NumPy, basically. Which is unfortunate, because it's like if you want to get the best performance in Python, you should reach for a library that might not actually be exactly what you want. You might not necessarily want arbitrarily ranked arrays, but it's going to be faster than Python.
Did you try PyPy?
I have not tried PyPy. So yes, I know PyPy. There's a couple different tools, I think, too, that you can use to try and kind of half compile, but I have not, no. So we're going to see Thrust to continue move up here. We're now at 100,000, which is the one that we saw. You can see now C++, the three of them are at the top. In this order, it's still C++ Flux, C++ ranges, and then C++ range v3, followed by Rust iterators. And note, it's hard to tell, almost invisible from here, so the odds are. But where my little cursor is moving is a Rust logo that represents the parallel iterators, and this is the non-parallel Rust iterators. If we move to 1 million, Thrust is now number 1. Flux is still the best C++, and parallel iterators are gaining. And note that NumPy and BQN are still better than Swift. Swift is kind of marketed as this systems language, but I would say that like Python performance is here, C++ and Rust performance is here, and Swift is in the middle. Swift is much faster than Python, but being halfway between Python and C++, a lot of the times, it doesn't cut it for what you are reaching for a fast systems language for. If we go to 10 million, Thrust is going to stay number 1. Parallel iterators in Rust is now number 2. C++ Flux is 3rd. And last but not least, when we hit 100 million, CuPy jumps into 3rd. And number 1 and number 2 haven't changed, which are Thrust and Rust parallel iterators. So if we zoom out on all of this, this is the summary of the benchmarking. Number 1 is always by C++ Flux or by Thrust. We can see that Swift progressively kind of declines. I guess Rust, it's the same thing. That's more, I guess, the effect that the GPU backends are getting faster the more data we get. And Python ends up being very poor. I saw a hand go up.
How did you optimize C++ code, and how did you use vectorization, for example?
I used -02, so I think vectorization is with -03.
Probably you need to explicitly turn on.
Yeah, so I didn't turn on any like fast math or any of the tricks for getting faster code.
Vectorization for this type of task is typically kind of useful.
Okay. So yeah, a question is maybe try this with vectorization. We might get different results. There was a hand go up over there.
I would say the same to enable vectorization in the same CPU.
Okay, yeah. So the same comment was enabling vectorization could change the difference. Any other questions while we're on this slide?
Do you happen to know why the C++ ranges perform
Worse than Flux? Yeah. So the short answer is go watch Tristan Brindle's C++ on C talk from I think 2 years ago or a year and a half ago. He gave a talk introducing this Flux library, and he also gave a lightning talk at CPP North, I want to say not this year, but a year and a half ago as well, where he explicitly showed this one example in 5 minutes of filter, because that's the classic example. So go watch those talks, lightning talk plus a talk, and you'll understand best. The slightly longer answer is that the models are different. So in ranges, when you are filtering, you basically end up with a find-if algorithm inside a loop, and it obfuscates the compiler's ability to see through that and optimize it as well as it could a single for loop that's doing like the same thing. It's a design issue, yeah. And interestingly, this is not really answering your question, but it's just a piece of history, is that the author of the library, Tristan, he actually played around with a couple different. So initially, his first library was Nano Ranges, which is a standard compliant implementation of the ranges library that was being proposed for C++ 20. So there was Range v3. I think Christabella might have had a ranges library. There was one at a Microsoft. Casey Carter was writing. And then Tristan had this Nano Ranges, which was only implementing what the standard was going to standardize for C++ 20. And then he went and wrote a second library that was inspired by different models. He called that one Flow, and I think he looked at Rust and their model. And then from that, after having implemented two different ones, he decided that like the best model was this one. It uses a technology called cursors. It comes with a lot more safety. You'll see that if you watch the talk. But on top of that, it also makes it easier for the compiler to reason about what it's trying to do, and you basically get the same compiler optimizations that you'll get when you're just writing the simplest for loop code, which ranges and range v3 in certain cases obfuscates its ability to do that. So like what Tristan likes to say is you always get as good as performance as ranges, and sometimes much better. More questions on this? All right, we got two more, and then we'll go to the conclusion, and we'll find time for a couple more questions. So yes. Rappel, yes. It's not open source yet. So the question was, what about Google's version of ranges? So yeah, there was a talk by John Bandela that was just given at C++ Now. I wasn't at the conference, but I saw it come online. I watched it immediately. I wasn't a huge fan of the API because I like the linear flow, and it uses kind of a inside out. But the API has nothing to do with performance. But at the end of the talk, he says it's not open source yet. So if we're interested, we need to get Google. We need to tell Google we're interested. So yes, this is another person saying I am interested also in seeing the Repel. As soon as Repel is open source, I will immediately add it to this project so that I can see the results. But yeah, until they open source it, I don't have access to the code. Another question?
Is the simple for loop in there in timing?
It is not. It is not. Technically, I could add that. Yes, but I have a. This is kind of all generated by a program that uses a DSL to generate this kind of code, which is why we were looking at like the 3 iterator example in Thrust and the 3 views example in ranges. So like what I actually do now is I write Python code that enables me to write a DSL that goes and writes all this code, because it is a pain to write, this many different versions of code, especially like it's very easy to make mistakes and then the errors that you get. So if you can just find a mechanistic way to generate this code, it's much easier. But yes, currently I don't have that. So we're going to come to questions. I just want to quickly wrap up with the conclusion, and then we'll have time for a couple more questions. So what is the conclusion of this talk? The number one thing, I think, at least if we're focusing on C++, is that prefer these fusion libraries. Like if you are a fan of Sean Parent's work and you like using algorithms, you now have access to these views, which technically are not, algorithms per se, but they give you the same, semantic, properties of being able to transform stuff, but you get the fusion. Like if you write 2 transforms in C++ 11 land, that's going to be doing 2 different passes, but now you can just pipe views together and you get that automatic fusion for free. I don't have to reach for transform reduce. I can just pass the transform view to a reduction algorithm like fold left, or in the case of the stdpar stuff, std reduce, and you get that fusion. If you have the ability, I would use Flux. I think Flux, maybe the jury is still out, but in my opinion, like Flux has won this war. It's the better model. You get better optimizations from your compiler. And if you go and watch Tristan's talk from C++ on C that was given a 1.5 years ago, it's a safer model as well. You don't end up with the dangling iterator issues that if you've ever seen Nico Yazudis' talks, he's got a litany of problems that he is not a big fan of ranges for. Flux doesn't suffer from these. I am less interested in the safety concerns and more interested in the performance concerns. But yeah, Flux is better in a couple different ways. Outside of C++, Rust tooling is amazing. I think C++ should learn from this. If we had as good a tooling as Rust did, I think that it's not going to fix the safety problems that the committee is working on, but I think that there's a lot of folks coming out of university that don't even consider C++ because the getting started story is so much better in Rust. Swift perf is, I might need to do some work. I'm not a Swift expert, but I was surprised when I did this benchmarking at how poorly Swift did to some of the other languages that we took a look at. If you are in Python and you are looking to accelerate your code without going to a GPU, half the time NumPy will get you, a performance edge. If you're doing stuff like that uses arrays and lists, think about just using NumPy instead of your built-in lists in Python because it's faster in general. And for GPU use, my recommendations are take a look at the parallel algorithm libraries that NVIDIA creates Thrust, or if you're in Python land, switch to CuPy. There's multiple options out there, but if you're getting started, I think these are 2 of the easiest ways to go from C++ code that you're writing today to C++ code that's running on the GPU, the same thing with Python. So with that, I'll say thank you, and I think we'll have time for 1 or 2 questions. Thank you.